Good afternoon. We are team puzzle bot number one, Rosendo, Hugo, Juanjo, Jesus, Ruben, and Jordan. Also, here we are with Victor, and our challenge has been to drive a small differential robot around a V-shaped track completely on its own. To succeed, we must detect the line markings and traffic signs, decide the correct maneuver, and execute the fast enough to hit 90-second lap target using the only board computations with no external whatsoever.
To master that shape, we kept everything on board, and NVIDIA Jetson running ROS2 receives the camera feed, process vision, and publishes motor commands. Two PID controller, DC motors plus a rear caster deliver the balance between agility and stability that curbs demand.
For the system architecture, basically we have our software has a pipeline with 5 layers. The first one is the camera input, in which we use the raw camera frames. Then we have a custom yellow V8 model that's got 7 traffic sign classes. Then we have a PID line following node that removes the lateral error. Then a behavior tree state machine that decides whether to drive slow or to stop or turn. Then lastly, we have the motor commands, which we use these messages to obtain the wheels.
To keep the robot centered, we filter the error with signals with a final media window and tune it with a derivative term to dampen oscillations. So first, we have a diagram with a Reno image, and that we rotate it 180 degrees and extract the ROI. Then we pass it to Whiskers and Gossamer to reduce the process. We apply an relative threshold and a global threshold and edge detections with CANI and erosion and dilation, and we connect the components and filtering to pass it to the state machine.
Well, we train a custom yellow V8 model for traffic signs detector and develop an HV segmentation to track the colors of the traffic light and keep track of 50 consecutive frames to avoid false detections, or algorithm translate these detections into commands as stop, turning, or following the line.
Our state machine built with PyTrees and includes 7 states: following line fast, which is the default, following line slow, stop, on left, on right, forward, and middle. Detections trigger transitions. For example, a yellow light activates follow line slow, and red light or a stop sign leads to stop. And turn and forward actions are executed once before resuming the line following.
In our challenges and solutions, we recount the false detections, the motor jerkiness, the PID anti-wind up limits, and multi-frame configurations. We identify these key during this development, and we reach them for obstacles to be completed and deleted.
In results, our last trial produced an 82.4% line tracking score and average a lap of 1 minute 50 seconds across 5 rounds with a sign detection f above 0.9 that play solid inside the competition.
This is team number 1, Puzzlebot, the autonomous car we've been working on. As an autonomous car that currently identifies the red light of the traffic signal, and when it turns green, it moves forward and begins to follow the black lines. When it detects that there is no black line at the intersection, it uses vision to detect the signs. We can see that it continues moving forward thanks to the detection of the forward sign. Once it sees the black lines again, it resumes following them and continues its path. Later, the camera can see from a distance that the black line ends and the bot reaches another intersection where it detects a right turn sign. As a result, the Puzzlebot makes a right turn even if it doesn't find black lines. Finally, after making the turn, the robot continues following the black lines, and upon identifying the stop sign, it comes to a halt, successfully completing the course with all signs properly identified.
So this was all from our part. This is how we contributed to the team, and as we can see, everything was effective and finished as its time. Thank you.